Welcome to section 8.10, which is the last section we're going to discuss in chapter 8. Remember, we're just doing a brief overview of chapter 8 so that we can get some things going. All right, so in section 8.9, we derived power series for some functions using geometric series, and that was great. Well, now we're going to have a more general procedure. Okay, and so we're going to look at this form of a convergent power series. Now, when we're looking at this power series, we've got our little sigma notation, our a to the nth term right here. When we're looking at the actual function here, you'll notice it looks very much like a Taylor polynomial. Remember, a Taylor polynomial, they're going to tell us where we stop. They'll say a fourth degree Taylor polynomial, or maybe they'll say find the first 5 non-zero terms. So we have a kind of stopping point so that we can use that polynomial to estimate or approximate other functions. Well, this is a power series, so it's going to go on. So you'll see that little nth term, so to speak, but then note you still continue on. So that's where that little plus dot 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 goes on, because we are going on. And note this is the form that every convergent power series is going to take. Now that convergence, okay, of a Taylor series, and because, just to back up, and because these coefficients are very much like a Taylor polynomial, they do call this a Taylor series. So that's why they say convergence of a Taylor series and not a Taylor polynomial. So when you're looking at that convergence, if the limit as n approaches infinity of that remainder, if that equals 0 for all of the x's in your interval, then your function converges and equals this guy right here. Okay? Now, like I said, this is a very brief picking of information of 8.10. So we're going to go right to some things that I think are going to give us more bang for our buck on the AP test. And that is looking at new power series by looking at those elementary functions and maybe adding some together, subtracting, multiplying, dividing, differentiate, and so forth. So we're going to look at a list, and this is a smaller list than the one that you have in your book. The book on page 638 has even more than I've got written here, but these tend to be the favorite. These are kind of the more elegant, more widely used basic power series. We've got 1 over x, natural log of x, e to the x, sine of x, and cosine of x. Now you'll notice when they talk about differentiating and integrating, well, if I were to integrate this guy right here, I will get this guy right here. And notice you have your x minus 1 to the second over 2. So when I integrated this, I'd get my x. I would have a plus c term. That c would be my 1, my negative 1. So very much like that problem we did in class where we ended up with this coefficient joining that first term so that we could get that same look going on. But we're going to be taking these basic power series and creating new ones. And let's see what that's going to look like. All right, so they might ask us to find the Maclaurin series, so we know c is 0, of sine of x squared. Well, remember that when it's sine of x squared, we're actually talking about the angle being squared, not the sine function being squared. So looking at our list, we know that sine of x is this series, okay? So really, if we're finding sine of x squared, we're just putting x squared into that same function, so we're creating a composition. So everywhere you see an x, you're going to slip in an x squared. So my new series becomes x squared minus x to the 6th over 3 factorial, and so on. Okay, so you get the idea. It looks pretty nice. Well, now we're working with this guy. And this one's a little bit more intense because we're working with e to the x times cosine of x. So if I look at those, okay, I've got this guy right here and this guy right here. I only need to have a few terms written down, so I'm not going to go very far when I multiply because this can quickly become an unpleasant situation. And you'll see what I mean. Okay, so I'm going to write the terms for the first couple players in our e to the x. So 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. Okay, so that's my e to the x, and I'm going to multiply it by my cosine, which is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Now note this keeps going and going, but we're just going to multiply out a couple terms so we can see what that pattern is. So when I multiply everything up here by 1, so let me do, okay, so I'm multiplying everything through by 1. So that's going to give me 1 plus x to the second over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. Okay, now I'm going to multiply by that next term. I'm going to multiply by negative x to the second over 2 factorial. So when I do that, I'm going to try to line these up with the guys I already have down here. So for instance, when I take this times 1, I'm going to have negative x squared over 2 factorial. When I take x times negative x squared over 2 factorial, that's going to give me negative x to the third over 2 factorial. This guy times the next one, that's going to give me negative x to the fourth over 2 factorial times 2 factorial. And then if I go to the next guy, okay, I've got this guy to the x, and you can see this is getting kind of big, so I'm going to stop here. Okay, I'm not going to go ahead and take it to the x to the fourth because it looks like I'm going to get plenty of terms here. And in fact, I'm going to stop even sooner on the next one. So x to the fourth, when I multiply that times my 1, I get my plus x to the fourth over 4 factorial. And then the next term, I'm going to take this guy times the x. That's going to give me positive x to the fifth over 4 factorial. And notice I've got plenty of terms here, so I'm not going to multiply any more of them. I think I've got a good representation right now. So when I add my columns straight down, I get 1 plus x. Look at your x squared terms. Those guys cancel out altogether. And then you have x to the third over 6 minus x to the third over 2. That's going to be negative 1/3 x to the third. Okay. When I look at my x to the fourths, I have x to the fourth over 24 minus x to the fourth over 2 times 2 over 4. And then that same guy over 4 factorial. So that's going to give me a minus 1/6 x to the fourth. And we can continue on if we'd like to. But we've got plenty of terms here, so if you don't want to do any more terms, you don't have to, and you can just put your little dot, dot, dot. Okay? So all we did to form this is a product of 2 of those basic power series. And we can get an idea of what our pattern's going to be. And a lot of times they'll just ask you to write out the first couple terms of that power series. So we'd have that under control. So some of them are less fun than others. That one was some multiplication. We'll say fun. All right, so now let's look at this guy. When I'm looking at, the first thing they asked me to do is to find that power series for sine squared x. So remember that sine x, and we're squaring that whole quantity, not like the composition we did before. So when we have sine squared of x, think about how we handled that when we integrated. We used a double angle formula, and we did it that way. So we're going to use that same approach. We're also going to split that apart into 1/2 minus 1/2 cosine of 2x. Okay? So we're going to start off with our cosine of x. Let's see how fast I can write this out, because I know you love short videos. So this is our basic cosine. Oh, fiddlesticks. I was trying to go fast, and look what happened. I made a mistake. Kids, you're just going to have to wait. It's going to be a long one. 8 factorial, dot, dot, dot. All right, so if I do cosine of 2x, that means everywhere I have an x, I'm going to put a 2 in there as well. Well, I don't want it to ruin the actual look of what I got, so I'm not going to put parentheses 2x parentheses squared. I'm going to go ahead and do my 2 squared over my 2 factorial x squared. And then I'll do the same thing over here. So this is going to be 2 to the 4th over 4 factorial x to the 4th. This is going to be minus 2 to the 6th x to the 6th over 6 factorial, and so forth. Okay, so now I want to multiply that whole thing by negative 1/2. Oh my goodness. Now when I multiply by negative 1/2, I'm going to be canceling out some of these 2's on top, because negative 1/2 times 1 is negative 1/2. And then when I take this guy, you're going to lose a 2 on top. And everything's going to change in sign. So now this one's going to be negative 2 to the 3rd over 4 factorial x to the 4th plus 2 to the 5th x to the 6th over 6 factorial minus 2 to the 7th, I'm sorry, that's annoying, 8 factorial, dot, dot, dot. Okay, so the only thing left to do is to go ahead and take 1/2 and add it to. So really the only thing that's going to change is when I add that 1/2, it's going to knock that 1/2 out. So I will be left with this final beautiful, and you can always simplify that. I'm going to leave it like it is simply because I can see the pattern better. And for me, it's just nice to have the pattern. So if they ask me to find the first couple terms of this power series, we are on it. But you can kind of see the thought process behind it. See if you can create the asked about power series by doing a composition, adding, subtracting some things from those basic power series. Please, 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 please start to memorize these guys right here. 1, 2, 3, 4, 5. Now, if you memorize them, you'll have an indication as to what they are. Maybe if you get some things to help you remember. If you remember your trig identities, remember sine is an odd function. Look, all the powers are odd. That might help you remember, you know, which series goes with which, so that you can snap those out pretty fast. Cosine is an even function. Oh, look, even powers. Okay, so kind of try to get some of those little things. I know some of you made up some really nice things to help you remember your how to test for your convergence and divergence. So keep those kind of things up, and remember, the sillier they are, the more likely we seem to be able to remember them. I'll see you in class.